Welcome. The purpose of this brief video is to introduce the concept of bias, or an alternative title might be, why are there two formulas for the standard deviation? Why are there two formulas for the standard deviation? Well, it has to do with the concept of bias. In common parlance, bias means that I'm inclined to interpret data one way versus another because of a belief I might hold, be it consciously or unconsciously. This is a focus on how data might be interpreted. In statistics, bias means there is a quote-unquote misdirecting trend in the algorithm or process used to analyze the data. In particular, it means an inference drawn from a sample about a population may be off by some amount over or under the true population parameter of interest. This is nothing specific to a given data set, but to the calculation being applied to the hypothetical world of all possible data sets. Let's start with an example of a process that is not biased. For our discussion here, we will use the term average to specifically be the arithmetic mean. If we take the mean of sample after sample drawn from a population, the average of those sample means will get closer and closer to the actual population mean. And that is exactly what we want with an unbiased process or procedure. There are various things in statistics that are unbiased. For example, like the mean of a sample, the median is also unbiased in certain circumstances. If I take lots of samples from a symmetrically distributed population and calculate their medians, the average of the sample medians is going to get closer and closer to the actual population median. Now, let's think about something that is biased. The classic examples are the minimum or the maximum. Let's focus on the maximum for a moment. If you take tons of samples from the same population and calculate the sample maximum for each, the average of those sample maximums will not get closer and closer to the true population maximum as you take more samples. Because the sample maximum is either at or below the true population maximum, most of my sample maximums will be below what they quote-unquote should be. In other words, below the true population maximum. And because it is simply impossible to get samples with maximums larger than the population maximum, there will never be any overly large sample maximums to quote-unquote balance out all of the underestimated values obtained for most samples. So, the average of these sample maximums will always be below the population maximum, regardless of how many samples we take from the population. This is bias. The long-run average of the sample maximums does not equal the true population maximum. In the case of the means, sometimes we had samples that were below the true population mean, sometimes we had samples that were above, and in the end they balanced out. For the sample maximums, when we take samples, the maximum will always be below, so there's no way for it to balance out, and there's no way for it to end up at the highest value that the maximum should actually be. It turns out that the standard deviation is similar in nature. It is a biased estimate. Without going into too much of an explanation why, we can extrapolate from the maximum always being underestimated in the same way the minimum is always being overestimated. This means the range will always be underestimated as the distance between the average maximum and average minimum will be smaller than it should be, and never larger than it should be. Well, in that the range is a measure of spread, other measures of spread, like the standard deviation, will suffer the same fate, if you will. For this demonstration for bias, I'm going to switch from talking about the standard deviation to the variance, which is the square of the standard deviation. This is being done for mathematical reasons, but the general idea still holds. Again, if we take the variance of lots of samples from the same population, and then we take the average of those variances, the average of the variances will not equal the population variance. Well, that is true if we use the population formula for the variance. This is where we divide the sum of the squared deviations from the population mean by the sample size, or in this case, the population size, which we will denote as capital N. Again, the formula for the population variance is the sum of the deviations from the mean divided by the number of data points in the population. Note, we use the symbols mu for the population mean and capital N for the size of the population. Now, if I calculate the variance from my samples with this same formula, that is the population variance formula, just replacing capital N with lowercase n and mu with x bar, on average, this population-based formula will give an underbiased estimate for the true variance of the overall population. That is, the average of the variances for each sample using the population formula will be less than the true population variance. But here's where the mathematics works in our favor. Though I won't go into the proof of why this is true here, you just have to trust me on this for now. If I redefine the variance for a sample using x bar for the sample mean instead of mu the population mean, and if I divide by a slightly smaller number, 1 less than the sample size, n minus 1, then I obtain this formula. The sum of the squares of the deviations from the sample mean divided by 1 less than the sample size. Thus, I have made all of my sample estimates just a little bit larger, and this mathematically removes the bias. Now, the average of the sample variances with this formula with n minus 1 does indeed get closer to the population variance for more and more samples. Thus, the sample variance is an unbiased estimate for the population variance, and we get the sample standard deviation from the sample variance by taking the square root of the sample variance. And this is why we have a formula for the population standard deviation, which is different from the formula for the sample standard deviation.